We now discuss a very important class of prefix codes called Huffman codes, which is a simple construction of optimal prefix codes. For the binary case, the procedure is very simple. Keep merging the two smallest probability masses until one probability mass, that is 1, is left. For the D-ary case, first insert 0 probability masses until there are d plus k times d minus 1 masses, if necessary. If the number of probability masses has this form to start with, then we don't have to add any 0 probability masses. Then, keep merging the d smallest probability masses until one probability mass, that is 1, is left. In general, there can be more than one Huffman code. Our remaining discussion will focus on the binary Huffman procedure. After that, we will discuss the D-ary Huffman procedure. Here's a very simple example of the binary Huffman procedure. Suppose we have a probability distribution with probability masses 0.35, 0.1, 0.15, 0.2, and 0.2. First, we identify the two smallest probability masses, 0.1 and 0.15. We merge them into one probability mass, 0.25. In the remaining set, we identify 0.2 and 0.2 as the two smallest probability masses. Then we merge them into one probability mass, 0.4. Now in the remaining set, which consists of 3 probability masses, we identify 0.25 and 0.35 as the two smallest probability masses. Then we merge them into one probability mass, 0.6. Now in the remaining set, there are only 2 probability masses, namely 0.4 and 0.6. And obviously, they are the two smallest probability masses, and we merge them into one probability mass, which is equal to 1. Now we have formed a code tree. By adopting the convention that going up is 0 and going down is 1, we can assign the code words accordingly. For example, the code word assigned to the probability mass 0.35 is the code word 00. We are now going to establish the optimality of Huffman codes. That is, the expected length of a Huffman code is the smallest possible. Without loss of generality, we assume that the probability masses are indexed in descending order. Denotes the code word assigned to Pi by Ci and its length by Li. Theorem 4.17 says that the Huffman procedure produces an optimal prefix code. Before we prove Theorem 4.17, we need to establish 2 lemmas. First, lemma 4.15 says that in an optimal code, shorter code words are assigned to larger probability masses. That is, L1 is less than or equal to L2, so on and so forth. Lemma 4.16 says that there exists an optimal code in which the code words assigned to the 2 smallest probabilities are siblings. That is, the 2 code words have the same length and they differ only in the last symbol. We first prove lemma 4.15. That is, in an optimal code, shorter code words are assigned to larger probabilities. Consider a probability distribution P1 up to Pi up to Pj up to Pm, such that Pi is strictly greater than Pj. Assume that in a particular code, the code words Ci and Cj are such that Li is greater than Lj. That is, a shorter code word is assigned to a smaller probability. Intuitively, by exchanging Ci and Cj, the expected length of the code should be improved. Specifically, let L be the expected length of the code, which is given by summation k pklk. We now separate out the term I and j, so we first sum over all k not equal to ij, pklk, and then we sum pili plus pjlj. And we let L prime be the expected length of the code obtained by exchanging Ci and Cj, so L prime is equal to summation k not equal to I and j, pklk, plus pilj plus pjli. Note that Li becomes Lj here, and Lj becomes Li here. Comparing L prime and L, we see that the summation in L cancels with the summation in L prime, so that L prime minus L is equal to pilj plus pjli minus pili plus pjlj. Rearranging the terms, we have pilj minus pili minus open bracket pjlj minus pjli close bracket. Now factorizing out pi, we have pi times lj minus li. Similarly, factorizing pj, we have minus pj times lj minus li. Then we factor out lj minus li to obtain pi minus pj times lj minus li. This product is negative because pi is strictly bigger than pj, and li is strictly bigger than lj. Therefore, we conclude that L prime is strictly less than Lj. Since the original code can be improved, it is not an optimal code. Therefore, for an optimal code, shorter code lengths are assigned to larger probabilities. The lemma is proved. There exists an optimal code in which the code words assigned to the two smallest probabilities are siblings. Consider any optimal code. From lemma 4.15, the code word cm has the longest length. Then the sibling of cm cannot be the prefix of another code word. This is illustrated in the figure. We claim that the sibling of cm must be a code word. To see this, assume that it is not a code word and it is not the prefix of another code word. Then we can replace cm by its parent to improve the code, because the length of the code word assigned to pm is reduced by 1, while all the other code words remain unchanged. This is a contradiction to the assumption that the code is optimal. Therefore, the sibling of cm must be a code word. If the sibling of cm is cm-1, then the code already has the desired property. That is, the code words assigned to the two smallest probabilities are siblings. If not, assume that the sibling of Cm is Ci, where I is less than m-1. Since the code is optimal, by lemma 4.15, we have Li less than or equal to Lm-1 less than or equal to Lm. On the other hand, since Ci and Cm are siblings of each other, they have the same length, and so Li is equal to Lm. Therefore, Li is equal to Lm-1 is equal to Lm. That is, Ci, Cm-1, and Cm all have the same order. Then we can exchange the code words Ci and Cm-1 without changing the expected length of the code. That is, the code remains optimal to obtain the desired code. That is, Cm and Cm-1 are siblings of each other. The lemma is proved. We now introduce the concept of reduced code tree. Suppose Ci and Cj are siblings in a code tree, then Li is equal to Lj. If we replace Ci and Cj by a common code word at their parent, call it Cij, then we obtain a reduced code tree, and the probability of Cij is Pi plus Pj. Accordingly, the probability set becomes a reduced probability set with Pi and Pj replaced by a probability Pi plus Pj. Let L and L prime be the expected lengths of the original code and the reduced code respectively. Then L minus L prime is equal to PILI plus PJLJ minus Pi plus J times Li minus 1. Now replace Lj by Li because Li is equal to Lj. Then factorize Li to get Pi plus Pj times Li minus Pi plus Pj times Li minus 1. And so we get Pi plus Pj. And this implies that L is equal to L prime plus Pi plus Pj. This relation says that the difference between the expected length of the original code and the expected length of the reduced code depends only on the values of the two probabilities merged, but not on the structure of the reduced code tree. We now prove theorem 4.17, which says that the Huffman procedure produces an optimal prefix code. Consider an optimal code in which Cm and Cm-1 are siblings. Such an optimal code exists by lemma 4.16 that we have already proved. Let Pi prime be the reduced probability set obtained from Pi by merging Pm and Pm-1. As before, let L and L prime be the expected length of the original code and the reduced code respectively. Since L is equal to L prime plus Pm-1 plus Pm, we see that L is the expected length of an optimal code for Pi, if and only if L prime is the expected length of an optimal code for Pi prime. Therefore, if we can find an optimal code for Pi prime, we can use it to construct an optimal code for Pi. Note that by merging Pm and Pm-1, the size of the problem, namely the total number of probability masses, is reduced by 1. To find an optimal code for Pi prime, we again merge the two smallest probabilities in Pi prime. This is repeated until the size of the problem is eventually reduced to 2. That is, the probability set has only 2 probability masses. In this case, we know how to solve the problem because an optimal code has 2 code words of length 1, regardless of the values of the probabilities. In the last step of the Huffman procedure, 2 probability masses are merged, which corresponds to the formation of a code with 2 code words of length 1. Thus, the Huffman procedure indeed produces an optimal code. This is illustrated in the example that we have seen before, where the 2 probability masses 0.6 and 0.4 are merged into a probability mass 1.